Good morning, everyone. Welcome to the lecture 1 of Unit 5. I'm sorry, this is for another class, it is Unit 1, and for your class, it is Unit 5 Slope and Deflection of Beams. So, first definition of what is slope and what is deflection. Let's see. What is slope? Slope at any point in a beam is defined as it is an angular shift at any point of a beam between the no load condition and the loaded beam. Its value is different at different point on the length of the beam. It is represented by dy by dx or theta. Its unit is radians. There is a maximum limit for a slope at any loaded beam. Okay, so this is the definition. It is an angular shift. You can consider let a beam. I'll show you with an illustration. Okay, let's consider this type of beam. In this beam, it is a cantilever beam with UDL and also point load. You can see that this particular beam will be deflecting downwards. That is, the B will be shifted to bottom point, which means that this uh, beam will be curved towards downward direction. That is, B will be shifted from top to bottom and C will be from C here to it will be shifted to bottom. So this is called as deflection. But at this point you can see that the horizontal beam have become somewhat slightly downward. It has been tilted downward direction. So that rotation is called as uh, simply slope. So it is an angular shift at any point of the beam between the no load condition and the loaded beam, which means that without load the beam will be horizontal, and then after the load the beam will start to rotate, and that rotation angle is called as slope. So it is represented dy by dx. So similarly deflection. So slope is called as angular shift and deflection is called as vertical shift. That is the movement of the position of any point vertical in the vertical direction is called as deflection. So it is denoted by y or delta. Its unit is mm. This also have some limitations. Then relationship between slope, deflection and flexural rigidity and bending moment. So for this, the first derivation is 1 by r is equal to d square y by dx square. Here x represents the horizontal direction and y represents the vertical deflection. Now differentiating 2 times the deflection with respect to x, you will get 1 by r. R is nothing but radius of curvature. R is called as radius of curvature. But also we know that this radius of curvature from the previous unit, you know that m by I equal to E by R. 1 by I, m by I equal to E by R. Rearranging this, 1 by R will be equal to m by I. Therefore d square y by dx square is equal to m by I, and this equation is called as slope and deflection equation. This is called as this is a differential equation, and we have to solve for this y value and find y value from this equation. So and this is called as the differential equation to find out the slope and deflection. Then there are 4 methods in finding slope and deflection. One is double integration, another one is Michaelis method, then moment area method, then conjugate beam method. So different in the name itself you can see that it is double integration method. So this equation you have to integrate it 2 times, so that one time when you integrate you will get dy by dx, and second time when you integrate you will get y. So we have to find out that y by integrating the equation. Michaelis method is also similar to double integration method, but it is more advantageous than the double integration because double integration have some limitations. Moment area method is specifically for cantilever beam alone. Then conjugate beam method is used to find out any type of methods. Now let's start with the double integration method. You can see that this is the differential equation we got. Integrating one time with respect to x, then dy by d square y by dx square will become, that is the d square y by dx square becomes d square y by dx square, which is equal to integration of m by ei into dx. This is nothing but it is called as slope or theta. Then integrating integrating the slope with respect to x, you will get that y is equal to double integration of m by ei into dx, and this is called as deflection. Then limitations of double integration method. This method is applicable for beams carrying single load only. Then it is not applicable for varied section, that is for different I value it cannot be analyzed. Then combination of different materials, which means that different E value cannot be analyzed, which means that for this integration purpose you have to keep I value and E value as constant throughout the length of the beam. Okay, let's start with the procedure. Step 1. First, find out the support reaction in case of simply supported beam, but in case of cantilever beam there is no need to find out the support reaction, that is RA and RB. Step 2. Take a section XX at a distance of x from the left any support, that is from the right support or from the left support, and find the moment about the section. Then substitute E value, I value and moment value in this equation. So before that, this moment value, you have calculated the moment about x axis, you have to substitute it here and substitute the value of E and I value which is given in the question. Those are constants. E is constant, I is constant, but m is the variable which will have x here. So substituting everything, again integrating with respect to x one time, you will get the slope along with the integration constant C1. You know that while integrating you will have integration constant C1. Then again integrating that you will get two integration constants, that is C1 and C2. Now the objective is to find out this C1 and C2. Apply the boundary condition. So this is the boundary condition to apply. You can see that for cantilever beam the boundary condition is x is equal to 0, y equal to 0. Then for the two boundary conditions, one is, that is you can see that in this cantilever at the support condition it is x is equal to 0, at the free end the x is equal to x is equal to L. So at the fixed support, that is when x is equal to 0, y is 0, y is deflection. You know that deflection is 0 at the support, and also at the fixed it will not rotate, which means that slope is also 0, rotation is also 0. At x is equal to 0, y equal to 0 and x is equal to 0, dy by dx is equal to 0. Substituting these boundary conditions in this previous equation, that is the first integration equation and second integration equation, we can find out the value of C1 and C2. So here for simply supported beam, you can see that x is equal to 0, y equal to 0 and x is equal to L by 2. This is L, small l, that is total length, that is support to support is L, so that the half the distance is L by 2. At that point the dy by dx is equal to 0, dy by dx is equal to 0. Then substitute with these two boundary conditions, you have to find out C1 and C2 by substituting in these two equations, that is slope equation and deflection equation. And then substituting the C1 C2 value, you will get the modified slope and deflection equations. Then substitute the x value and find the slope and deflection at any point for the simply beam. So this is the standard procedure for finding. So this is the procedure for both double integration method and also this is for a double integration method and also for the Michaelis method. Next, so let's see with an example problem. It is similar to the derivation here, that is to find out the slope and deflection at the free end for this cantilever beam with the point load W at the free end. The length of the beam is L.
So first step, you have to take a section xx at a distance of x from, I am taking from the support thing, and then the balance length is L minus x. E and I are constants throughout the beam. So first step it is to find out the moment value. So moment about this x point. So for this x point, I am going to take the left side of x, that is w into L minus x. This is the perpendicular distance L minus x, and w is the load. So w into L minus x. You can see that moment is equal to minus w into L minus x. So now this is the equation, slope equation. Sorry, this is the differential equation, that is d square y by dx square is equal to m by ei. Substituting this m value here, I am getting this. Now rearranging this, ei into d square y by dx square, because e into I is constant, which is equal to minus w into L minus x. Then integrating with respect to x, you know that while integrating ei into dy by dx is equal to, here w is constant, L minus x is the variable, so L minus x the whole square divided by 2, and again differentiating into minus 1. So after integrating, you will get an integration constant c1. Then again integrate this in with respect to x. So ei into y is equal to minus w into L minus x whole cube divided by 6. That is this cube becomes cube will come to the denominator, so 2 into 3 equal to 6, plus this is a constant. While integrating a constant, you will get one x value, and then another constant will be coming. So these are the 1 and 2 are called as slope equation and deflection equation, because y is deflection and dy by dx is slope. So it is called as the respective equations, slope equation, deflection equation. Then boundary condition, it is a simply supported beam. So x is equal to 0, y equal to 0, then x is equal to 0, dy by dx is equal to 0. Now substitute these conditions in equation 1 and equation 2. After substituting, so ei dy by dx is equal to 0, which is equal to w into, you can see that here w L minus x, x is substituted as 0 now. So w L square by 2 plus c1. So c1 is equal to minus w L square by 2. Then substituting this is the second equation, that is x is equal to 0, y equal to 0. In the second equation here, x is equal to 0 and y equal to 0. Substituting that, you will get it is 0 equal to minus wl cube by 6 plus c2. So c2 is equal to wl cube by 6. You can substitute the c1 value here. Then after substituting this c1 and c2 in the equation 1 and 2, you will get ei dy by dx is equal to wl minus x the whole square by 2 minus wl square by 2, and then ei y is equal to minus wl minus x the whole cube by 6 minus wl square x by 2 plus wl cube by 6. So this is the slope and this is deflection equation. Now we have to find out the slope at free end, that is B point, free end at B point, and deflection at the free point. You can see that at B, L is x is equal to L. In the diagram, you can see that at B point, that is at A point, x is equal to 0, and B point x is equal to the full length, that is L. So substitute x is equal to L in this equation. Substitute in the slope equation, substitute x as L, and you will get the equation as WL square by 2EI. Then substitute the x value as L in the deflection equation, and you will get the deflection at the point B. So similarly, at which point you need that, at that point you need to calculate the x value and substitute the x value. Then next thing is a cantilever beam with UDL throughout. Now also we are going to find the slope and deflection at the free end. This is also a same procedure. So you can see that we will take a section at a distance of x from the support. From the support you will see, and then that is x and other is L minus x. Now mx is equal to minus w into L minus x into L minus x by 2, which is equal to w L minus x whole square by 2. Then slope is d square y by dx square is equal to m by ei. So substituting the m value minus w l minus x whole square by 2 ei. Then integrating this, you will get a minus this value and plus c1. Again integrating this, you will get c1 and c2. Now boundary condition, x is equal to 0, y equal to 0, x is equal to 0, dy by dx is equal to 0. Substituting these two in this both the equations, you will get c1 and c2. Then substitute the c1 and c2 in the equation and write the modified slope equation and modified deflection equation. Then at the free end, x is equal to l, and at the free end, x is equal to l, substitute in equation, that is slope equation and deflection equation, you will get the following corresponding values. So here for cantilever with UDL, the slope at free end is WL cube by 6EI, and for deflection it is minus WL power 4 by 8EI. This is another thing. I am showing that for a cantilever beam with point load at a distance of fixed, you can see that here the point load is at some distance, not in the free end, but it is in between the A and B. For this, you can see that from A to C, it will deflect curved path, and then after that it will deflect in a straight line. You can see that it will deflect in a straight line. So at point C, you can see that at point C, the deflection is YC, and that you can substitute this one. You can see that here the length is A, that is distance AC is nothing but small a. So substitute in this equation, that is, this is a formula. You can substitute L instead of you can substitute A instead of L here, and write the same equation for YC. And then to find out YB, you have to see that there is a triangle here. It is formed a right angle triangle, and here YC is minus WA cube by 3EI. Then sorry, this is for a UDL and this is for point load. Point load is minus A cube divided by 3EI, and then YB will be equal to YC plus L minus A. What is L minus A? The remaining distance, that is BC distance into the slope, that is the horizontal BC distance into the slope. Slope is nothing but this theta. So theta into the horizontal distance, you will get this vertical distance, and then already you have YC. So adding both these two, you will get total YB value. So this is the total YB value for double integration method. So thank you. I will explain the problem in the next lecture.